Hello, everyone. I'm Sara Libanore. I'm a postdoctoral fellow at the Ben-Gurion University of the Negev in Beersheba, and I'm an astrophysicist and a cosmologist. I guess there's no need for me to tell you why I was always fascinated by the universe. We're all used to see these very, very beautiful pictures coming from space telescopes or Earth telescopes, showing us all these galaxies and stars that shine on the darkness of the night sky. But this is just the end of the story. This is the universe, how it looks like today. And yes, I put the same dress on to emphasize the point. So the universe, as we see it, is around 14 billion years old. It's a very old universe. It went through a lot of processes. And one of the main questions is to understand how was it back in time? How was it at the beginning? How was it when it was a child? This picture is very, very different from the previous one. And it shows us a universe that is completely in a different state. There are no stars, there are no galaxies. Here, the universe is almost filled by neutral gas. It's very packed. Everything is very close by. There are just some patches that are more dense or less dense. What happened? How did we go from there to the galaxies and stars? One way to find the answer to this question, the way that I'm following, is to look at the universe in an intermediate state, to look at the universe when it was a teenager. Here, we want to understand how the universe was when the first stars and galaxies formed. How we went from the neutral gas that formed gas clouds to the formation of stars and galaxies. This image is not so straightforward. We're going to go through that. We're going to discuss together how to interpret what we're looking there. And to do so, we need to move across two different fields. On one side, to understand how do we observe the earliest galaxies, we need to take into account astrophysics. Astrophysics is what the science that is looking at how sources form, how they emit light, how galaxies form. On the other side, we have cosmology. Cosmology is more interested in the universe as a whole, on the universe on the large scales. We want to understand what are the components of the universe, how it changed across time. Combining these two fields, we want to understand what happened, how the universe changes phase, how we can explain the earliest galaxies, the teenage universe. So once upon a time, there was just gas, neutral gas, and the gas undergoes the effect of gravity. Gravity attracts the gas, and in the places where all the gas fall, the density increases. And there, the condition is good to form stars. The stars start to shine where the density is high. And if they shine, if they emit light, they are able to ionize the surrounding gas. The ionized gas emits lines, the same lines that chemists in labs can observe. By looking at these lines, we can infer information about the first stars and galaxies. But all these stars and galaxies are so far from us, they are so faint that we are not able to see each one of them separately. What can we do then? We can collect the full light. We can measure their integrated emission, so the light coming from all the stars and galaxies in one patch. And from that, we can analyze in a statistical way our image to understand what we are looking at. This technique that collects all the light from all the sources in the field of view that we're looking at is called line intensity mapping. Line intensity mapping is a very young field. So young that we still don't have a lot of data. We don't have all the images and pictures that galaxies people have and can observe and analyze. We are still at the stage in which we are trying to understand how to build our experiments, which kind of information we can get from this field, how to bring together astrophysics and cosmology to get data from this kind of images. So what can we do if we don't have data? We can prepare for the data to come. There are people that are studying how to build experiments, how to increase our ability to observe these kind of emissions. What I'm doing instead is to try to guess what we will see when we will get this data. We are trying to model the signal, to, let's say, guess how the signal should look like based on the knowledge that we already have from our models. So since in each batch I told you that we are collecting light from many kind of galaxies, from many sources all together there, to guess the amount of light that we're going to get from there, we need to know how many galaxies there should be. How many galaxies can form in that patch of the sky? This is an information that comes from astrophysics and from a quantity that is called star formation rate. How many stars can I form? But this information alone is not enough, because galaxies doesn't form all over the place. They form in specific part of the universe. They form inside what we call dark matter halos. I did it on purpose, because you have to get the dark matter halos. Okay, so dark matter halos. We don't know dark matter what is. I'm not entering this discussion in this place, but we know what is the effect of dark matter. Dark matter produces gravity. And gravity, as I told you, attracts the gas. So wherever there is dark matter, there is where galaxies form. Dark matter forms these clumps that are called halos, and inside those halos, we have the galaxies. So if we observe the galaxies, we can understand where dark matter is. So we want to combine the information on the star formation rate, we want to combine the information on the distribution of these dark matter halos, and we want to predict the signal that these line intensity mapping surveys will observe in the future. But what will happen if the signal that we will observe will turn out to be different from what we would expect? Well, you can guess the answer. Either we have more galaxies, so we will need to correct our astrophysical models, or we have a different number of dark matter halos, or we have halos that form galaxies in a different way with respect to what we were thinking. So the information that we will get, comparing the forecast that I'm doing now with the data that will come in the next years, will tell us whether we are getting the correct model or some errors that needs to be corrected. So on one side, we need astrophysics. On the other side, we need cosmology. Together, these fields can tell us, with their synergies, how the early galaxies form. And the early galaxies, through line intensity mapping, can help us better understanding all the models behind our knowledge of the universe. This is what I'm studying, and the data will come in the future. Let's wait for them. I hope I'm not going to be too old than this. Thank you for your attention.
So Carlos Bravo from Hebrew University of Jerusalem. First of all, congratulations, excellent presentation. As someone who is really into documentaries on the universe, I really enjoyed it. I have a question, which is, I understand that we have limited information currently about what early galaxies look like, but I was wondering whether there are any regions currently in the universe where the processes that are happening are relatively close or similar to the ones that were happening at the very beginning of time, so to say. And the reason why I'm asking this question is that I assume that if you want to look at how the universe was at the beginning of time, you have to look at very distant galaxies. Whereas if there are regions currently where this is happening, you can look it up from a closer distance. So is this possible or not?
Thank you, Carlos. Very good and interesting question. So you're asking about star formation in the end, right? So where do stars form? Stars form inside gas clouds that need to cool, and when they cool, they collapse. And at the center of these regions, the star can reach the density high enough to form and start ignite. Okay. So there are still star-forming regions that exist in the adult universe, let's say, in the universe today. So for sure, by looking at those regions, we can better understand the processes that went through. When we go to the earliest universe and the earliest galaxies, the process is kind of the same, but the kind of gas that was available at that time was a bit different. Because you may know that the most abundant element in the universe is hydrogen, and with a tiny abundance of other elements that are mainly produced during star formation and star evolution processes. So stars that form today form out of gas that is full of oxygen, carbon monoxide, and so on and so forth. While the first stars and galaxies form in a gas that was still quite pristine, let's say. So mainly hydrogen, some metals, but very few. So the process is the same, but the conditions were different. So also the properties of the stars and the galaxies that you formed at the beginning was kind of different. For instance, we discuss about this, they're called population 3 stars, are the first stars that were formed. Those were just made by hydrogen and maybe a bit of helium. And that to support such kind of process, the stars had to be way bigger than the stars that we have today. So for sure, by looking at the local and recent universe, we can understand better star formation processes. But then we need to take into account that the state was not the same, actually. Sure.
So, thank you. So there are no regions currently where stars are forming with the gases that used to be used?
Mainly not, because the gas was already processed by older stars that were in the field in the previous year. Thank you for your question.
Hi, Sarah. This is Maria from Technium. Thank you so much for your presentation. It was really interesting. When you talk about getting result in a certain amount of time, I was wondering how much amount of time, and if it depends, of course, how far these young galaxies are from the Earth, or what about this? Can you tell us more?
So thank you for your question about the timescales of our experiments. So regarding what I'm working on at the moment, the problem is just a matter of we are waiting for the instruments. For instance, this nice picture, the red and orange, this is from a simulation, not from a real picture, from galaxies that are observed when emitting a CO line, so carbon monoxide. To observe that line at these distances in the universe, you're looking at gigahertz band. Okay, so you need antennas in the end. The antenna that is studying that kind of emission is operating since a couple of years. We have the first bunch of data, but we need more to be able to do proper science, right? So the time scale is just related with the number of detectors that we can build, the number of antennas that we can place all around. And it's a matter of technology, but it's also a matter of understanding more and more how to improve our instruments.
Sorry, I have a second question.
Sure.
Is this technology related in some way, for example, when the researchers got this first picture of a black hole, is related in some way?
Okay, very good point, because also the picture of the black hole was produced starting from radio observation. But in that case, what you need to do is to, it's called interferometry. So you need to take into account the information coming from different detectors, and because radio waves are not able to show you like a point. So you need to take into account the way you're observing from different positions and to rebuild the image. While here, this kind of picture here can be made also without this interferometry technique. You just need to collect all the light. But yeah, the instruments are quite similar, because in that case is radio, this is like microwaves, so more or less the length is the same.
Thank you.
Thank you.
Herman from Hebrew University. I mean, just like to focus on the criteria you use to choose your picture. As we know, universe is growing, so no one knows its limit. And how did you choose a picture? Which tool you use? JSON Web, and which part of universe did you take that picture?
Thank you, Herman, for your question. You're right. We cannot observe actually the full universe at the same moment. We build up maps, and depending on the detector that we're using, there are detectors that can observe a wide field of view, so very large patches, and detectors that observe a small field of view. So for instance, these two images that I was showing previously, the Galaxy one and the like patchy one, they are showing the universe not only on a very different moment, because galaxies are quite recent, while the other is like 400,000 years after what we call Big Bang, okay? But they're also showing you different size of the sky. We are able to observe the full sky if we use instrument like a radio antenna, okay? While with optical telescopes, we can only observe patches. Which patch do you observe? It depends on what kind of science you want to do. For instance, for people that study galaxies, they're very interested maybe in regions in which there are a lot of galaxies, and so they can have high statistics, but also they can see like correlations between their shapes or their position in order to infer also properties of the environment. But if you're studying, for instance, the, I don't know, the property of, I don't have a direct example in mind, but maybe you can observe a patch that is more dark because it's more related with far objects that are more faint, and so you can be able to resolve them. And then, as you said, there is the problem that the universe is expanding. We don't see this on the time scale of our life, let's say. So at this moment, the universe at this size, and for all my life, it's gonna be that size because the time is very different, right? But still, the very fascinating thing in this field is that you're able, by changing the kind of light that you're observing, either you're observing optical or radio or infrared or ultraviolet, etc., you can observe different processes, but also you can observe the universe through time. The further you look, the backwards in times you're looking at. And in this way, you can also trace the way the universe expands. I hope I answered your question. Thank you.
Hi, Jan from Tel Aviv University. Thank you for the great talk. I would have a question on what are the main challenges to measure that light, which you call line intensity mapping.
Mm-hmm. So thank you for the question. So challenges in line intensity mapping. Line intensity mapping is, so it has pros and cons. As you can see from the image, you're not able to observe single objects, right? This is a problem. This is a problem because you cannot count the galaxies that you have. You only have an integrated emission. But you can use it as a probe. You can use it to understand more because you're more sensitive, for instance, to faint sources. If you were able to observe just the brightest galaxies, yeah, okay, you can have some information, but you are biased because you're just measuring the biggest, the brightest, the most massive, right? If you get the full information, that's true, you're not able to locate each one, but you can have information also on the faint one that maybe give you a small amount, but still you're able to measure that. That's one thing. Then the other thing is depending on the frequency that you're observing. Since here you're observing around like gigahertz, but our technology is good enough to probe megahertz or even less, you're able to chop this measurement. I'm talking this way because, you know, more or less you're in the field. You have a very good redshift tomography. So you're able to see this signal evolving across time. Thanks to the kind of technology that you can observe. On the other hand, since you're observing frequencies, you can also have emissions from stuff that are between you and the thing that you're observing. These are either called interlopers or foreground. To see the galaxies and sources that are far, far away from you, you need to get rid of whatever is between you and the source you're looking at, right? And that's a huge problem. Then depending on the frequency you're observing, this can be either more or less relevant. And finally, the last but not least problem is that since you're observing these frequencies, you have emissions like radio emissions that we use to communicate via phones or to watch television, etc. They produce signal that enter our detectors. So how can we able to get rid of this? We place detectors in very weird places, usually in the desert, or there are people now that are discussing of placing this kind of detector on the moon, since we're all interested in the moon. And yeah, these I would say that are the main points.
Thank you very much for the answer.
Thank you.
Okay, Sarah, thank you very much.
Thank you.